The big thing with calculators are scientific calculators and TI graphing calculators. They both understand order operations, which kind of sucks for humans because we'll put something in incorrectly and the calculator will do what we told it to, and then we'll get upset when the calculator tells us the wrong answer. So, I mean, the biggest mistake I always see is if I have to do this, right? So somebody puts in the calculator 4 minus 2 divided by 5 minus 7. What's the big problem there?
It's doing 4 minus 2 divided by 5 minus 7.
Divide first.
Yeah, it's going to divide what? It's going to do this first because it's going to follow order operations, right? So, to be honest, this is one of the most evil formats, believe it or not. This is a really evil format. This is the only time you see the big division bar. We see it all the time, but does the calculator see a big division bar? No. Thank God it has no eyeballs. I can't just point it at something, right? Because then the next step to take over. Yes?
For that, wouldn't you want to put parentheses?
Exactly. So whenever there's a long division bar, there's an understood parentheses that designate the top and the bottom. I love it. Okay. So the last little part about section 4.1 talks about some discrepancies when you put stuff in. Does everybody, what kind of calculators do you guys have? I have a scientific calculator. And some of you guys have a TI. Right? Does everyone know where their exponent button is? What I call the to the button? Yeah, so in a lot of calculators, on this one, on yours, it's a little caret, a little up arrow kind of thing. Does anyone have one that's like, says x to the y? Yeah? All right, as long as everybody knows how to use it. Okay, I like it.
Y to the x.
Y to the x, 11. 2. And I don't think there's that much more there, to be honest. Yeah, so they have some order operations you have to do in your head, and then they ask you to do it in the calculator. Blah, blah, blah. Okay. So, what we're going to start with then, we're going to get into section 4.2. All right. Which is where some nifty things happen. Okay. What's really weird to me is we've played with base 3 manipulatives. We've played with base 5 manipulatives in here, right? The little longs and the flats. I have all I have at my disposal for the actual number system that we use, base 10, is one set. So it's all for me. So I want to show you a couple of things using base 10 manipulatives. So I've got, of course, I've got flats. What does this represent? What number does this represent? 100. I like it. 10 by 10. Rectangular array. Okay. And then we've got a long, which of course is 10. And then, just to go against the color scheme, I've got a bunch of yellow ones. I like it. We're going to do a couple things up here. A little bit out of order from what this section does, but I don't care. We can do it. All right. Put you somewhere. There. Okay. Is it up there? Yeah, it's me. Okay. So what number is this? Oh shit. I love you guys. Hold on, let me zoom out.
125.
Yeah, 125. I love it. So, what if we wanted to do? Let's see what's the best way to do this. I know. We'll do it live. There it is. So, what if we wanted to do 125 plus, what do you got, Jeff? 67. 125 plus 67. So of course that means I'm going to slap down here 67. Let me see how far can I go? There we go, there we go. Stay. Okay. So 60. 7. I feel like that little dude in the video. Okay. There we go. All right. So if I want to add those two things, why are you not zooming out more? Oh, because you're absolutely at the extreme. Okay. So there's 125, and this is 67. I like it. So how would I add those? I mean, this is kind of nice. Can you imagine very young people just playing around with these things? All you have to do, of course, is just this, right? So far, so good, right? I'm just adding them together. So this makes complete physical sense. So, but what happens when I do this? Yeah. Let's see if we can do this real quick. Oh, it's exciting watching Jeff doing this. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So of course I could replace that with. Look at that, that was nifty. Sorry. Alright, so now you can see what the answer is. Maybe if I can make it a little bit better for you. Try to do it too. Okay. 100, 3, 6, 9, 192. All right, thank you. I know back up my numbers on it. Please tell me I didn't make a mistake. All right, now real quick. Okay. That's very, very simple. But again, this is simple because we know how to do it just directly. So of course, if you add visual aids, I'm like, holy shit, I'm all over this. It's base 10, right? It's not base 3. It's not these little freaking, not base 5 shit, right? This is base 10. So it's easy as hell for us. But it's really, really nice for people that don't know our number system because it's something to play with, something tactile. They can see it happening. Okay, now, what about subtraction? What are we going to have to be careful about with subtraction? Let's try an easy one first. So what if I had, oh look, I made some more of these in case I needed it, because I didn't have so many of those. All right. What if I had 42 minus 20 this, 27. I like it. So 42 minus 27. So what do I have to do visually here? Is this going to work? No, because when I can take, now this makes sense. Subtraction meaning I'm going to take this many away from this, right? So far everything's fine. Somebody write that problem down for me. I didn't write it down. What did I say? 42
minus
27. 42 minus 27. So if I take these two away, then I have a problem, right? So this is the first instance that a student will start to understand the idea of what? Because what are we going to have to do here? Borrowing. So I've got to kind of take one of these and get a really small hammer and break it down and drop it and make 10, 4, 6, 8, 10. Or are you sit there thinking, I never thought this semester I just watch a math teacher counts little yellow blocks. That was not what I thought was going to happen.
I did not expect it.
What's that?
I did not expect it.
You did not, okay, you didn't even know to not expect it. I like it. So now I can do this, right? So now this is going to be, so this is 7. So if I take 7 away, then I'm left with 15. Thank God, that's the right answer. Yay. But again, it's a very cool visual, yes? The whole idea of borrowing, I've actually seen people that don't really understand what they're doing, they just sort of do it. They don't really know why it works the way it does. So this is really cool for people that have never done it before in their entire lives, right? because there are only 7 or 8 or whatever. Okay. So what's the ultimate, okay, let's try this. What about multiplication? How would I do that? I had an example somewhere. That would work. Well, anything would work. All right, let me stop for a minute. Addition, subtraction. You can imagine that. You can see that with these manipulatives pretty easily. All right. So how would we do something like multiplication? So if I had to do 23 times 2, would be a very simple, yes?
Make another 23 to do 23.
Yeah, exactly. So one of the most basic ways is to bring back in the repeated addition. I love it. But again, you're doing it sort of like visually for them. What about, let me see, okay. What did I just say? 23 times 2. Okay. Let's see. Do we want to, well, okay. Let me do one more thing up here and then we'll switch over to some notes. So one way to do multiplication is to do something very similar to repeated addition. There is another way to do it. What about division? Okay. What about division?
What about it?
So much. What if I had 300 and 43, and I want to divide that by 2. Say again, sir? Yeah, we're going to create, so the next step to this, when we step away from manipulatives, is going to be trying to create algorithms. So when I say the word algorithm, what do you guys think of? Because that's sort of like where you're going. What comes to mind when I say the word algorithm?
Patterns.
Patterns?
Formulas.
Formulas? Anybody else? Anyone know any computer programming? No? Okay. I think computer programming. Algorithm is just a step-by-step procedure for doing something. So a recipe is an algorithm, right? For example. So let's think about this. If I wanted to divide this by 2, what does that really mean? Let's get really freaky for a second. So 10 divided by 2 is what? 5. Because for every group of 2, you make it 1, correct? So division by 2 is asking how many groups of 2 are in this thing. Stay with me, this is kind of cool. We're going to actually kind of go in the direction of how we do long division. And you're all like, oh, today is my favorite day so far. Okay. So we're actually going to kind of build our way to long division. So when you divide by 2, you talk about how many groups of 2 there are. So let's start with the biggest things. How many groups of 2 do you see in the flats? Don't you see one group of 2? Okay, so let me keep track of this. I can't even keep track of my pen. I want to keep track of the problem. I have no idea. Okay. So I've got 343 divided by 2. So I've got one group of 2 hundreds. So that is so far 100. What can I do with this guy then? What do you think? Because I want to move to the next shape. So I want to, I'm sorry, can I say? Yeah, separate this bad boy, right? So let me see. This is where I'm going to need some help. 1, 2, 3, 4, 5. Well, do I have enough, Jeff? Yes, I think I did just enough. Here come my special ones. 6, 7, 8, 9, 10. Okay. So now I've got 14. So how many groups of 2 are there in 14?
7.
Yeah, there's 7 groups of 2. I love it. I think I don't have to act. There it is. Yay! So let me write that down. So when I move to my 10s, I get 7 groups of 2 10s. So that's another 70. And then what do I do with this? How many groups of 2 are there? One group of 2 with remainder 1. Holy shit, so I get one group of 2, remainder 1. So this will be 171 remainder 1. Which is the right answer, correct?
Yeah.
Thank God, okay. All right, let me stop for a minute. That's kind of nifty because we're doing several things. We're doing a visualization of division, which before today, you might have thought, how the shit would that look? We're reminding people that dividing is actually asking how many groups of this many. So if I divide something by 7, I'm asking how many groups of 7 are in this number. Yes, maybe? Okay. You okay?
Yeah.
Okay. All right, so let's transition a little bit. We'll come back to more of this here in a minute. I want to be able to draw up here a little bit. So the whole thing with section 4.2 is trying to make sense of why the algorithms we use, to make sense of how to spell. I think you messed up again. Why they work. So we all know the long division algorithm. Now what do I mean when I say that? We put the number out front, we draw the little symbol, we know what to do, we subtract and we keep going, right? So let me take a step back. With addition, we could do it with the base 10 manipulatives. I want to add extra stuff to everything. So that's where we have the flats and we have the longs and we have the dot, blah, blah, blah. And we can just add them together. Okay. Has anyone ever seen Abacus? With the way you do the beads and you flip the beads back and forth. Have you guys ever seen those before?
Yeah.
You can call it Abacus. Abracadabacus. Hocus pocus. Yeah. Alright. So there's something called a chip abacus that you could use. But basically here. Alright. If you've ever seen an abacus, you know there's somebody moving beads back and forth on there, right? Does anyone have any idea what they're doing when they're moving these beads back and forth? All right, so here's the idea.
Tracking.
Color, you know how some have different colors?
Yes.
The colors mean something?
Maybe, it depends. There's a lot of different types, but this specific one I'm gonna look at is broken up into base 10 elements. So like 10 squared, 10 to the first, in the ones place. So if I wanted to represent the number 342, this would be 3 dots here, 4 dots there, 2 dots there. So you can kind of move it around. So you got 3 kind of places, so you know what they represent.
The 2 looks like an exponent.
This 2 here,
Mm-hmm.
it totally is,
Oh, wait.
right? Isn't this our places? 1s, 10s, and 100?
Yeah, I don't know why it's a 3. Oh, wait.
It's just between right based on the numbers.
Oh yeah, so 342 is 3 hundreds, 4 10s, 2 ones.
Oh.
Okay, cool.
That makes more sense.
I like it. So then if I wanted to do something like 342 plus 125, right? So this would be 1, 1, 2, 1, 2, 3, 4, 5. You just scan down real quick and see what that is. All right, so this would be 467. Crazy. So that's so close to what we do anyway, correct? It's almost exactly what we do anyway, just represented with little beads, right? So instead of having flats and so forth, they are actually place systems. The ones that come here are in the hundreds, tens, one, so forth. Okay. So those manipulatives that I use, the places are represented by the shapes. You want to bank this way over here? Yeah, let's do that. And then, of course, we get to our place value, which is just the way we do things. Right, that would just add. Now, real quick, we're not talking about decimals yet. Right, and of course, this is just, of course, all right, but side note. I really want this to make a lot of sense. I don't know how many of you guys have consciously considered this. How do you add this by hand? Jeff, just put it in a row. Right, what would you do to add that by hand? Line them up according to what? Decimal place, correct? You don't just kind of like put them wherever the hell, right? You wouldn't put 1.72 here, would you? That is crazy. So I could put 43.25. Why do we do that? Sure, place value. It's a very, very basic property. What's x plus y?
X plus y. No, we
Don't
don't.
know. And what's x plus x? 2x. Okay, I like it. So I can add, what's 1/10 plus 1/10? 2/10, right? So as long as if I line them up according to what place they're in, they're like terms. I got so many hundreds plus so many hundreds, so many whatevers. That's why the decimal place rules where things go, because it lines up what place everything is in. It's a very small little side note, but not many of us consciously think about that, right? Okay, I like it. And of course, that's what it is. Yeah, let's talk about, okay. So what about, so I've got manipulative method, which is kind of a very visual regrouping of things. The Abacus method, which is almost the same as what we do, that algorithm, right, the Abacus method. Okay, let me take this away. There's nothing that profound up here, so if you're looking for profound, it's not really there, but these are all, especially the manipulatives method, is really nice to think about how that's going to show kids how things work. What about, let me see, there we go. So what if I was going to do this? 37 plus 46. So if I was going to do the base 10 manipulatives, why do I want to make that 110? I have no idea. I would have 37 and 46. And then what would happen if I add those together? I would get 1, 2, 3, 4, 5, 6, 7. But what happens here? So I get 7 and then 6. And is that okay? Obviously not, right? So this is another, and again, you would do this with actual manipulatives, right? But you can see the idea here. So what do I group up here? I would group up 10 of those. This is my little malformed cookie. And I would make those into a, what? Yes, what is it called? A long, right? I like it. So now I got 1, 2, 3, 4, 5, 6, 7, and then there's an extra long, and 1, 2, 3. Now, this leads to something interesting. What is this the reverse of that we just did a minute ago? What is this the reverse of? What is this the opposite of? I'm collecting 10 from here and making it 1. What is that in reverse?
Opposite of borrowing?
Opposite of barring, exactly. I like it. So this would be a great place to kind of, again, whenever you're teaching people about anything, you want to try to connect what they know already with what they're about to discuss. This is a great connection point between addition and then subtraction requiring borrowing. So visually, this makes a ton of sense. The freaking long is 10, so if you ever get 10 little dudes, you might as well put a long in there. It kind of represents the same thing, so they catch on to that pretty quickly. But you want to look for things that'll kind of connect with where you're about to go. And borrowing is a really freaky deal for most people. Let's see. Yeah, those two are basically the same idea. But what happens a lot with students, what do you think somebody might put down for this if they're not really used to doing this? What do you think they might put down? 3 and 4 is 7. 7 and 6 is 13, right? All right, so this would be weird. How could you try to describe to somebody that that's not quite right?
6 is over 10.
Say again?
The 7 plus 6 is over 10.
Yeah, exactly. So you can attack it from a what belongs in our place 10 system. 13 doesn't have a place for a single digit. What's a less kind of detailed way to talk about it? Like if you say, well, what's 40 plus 40? They'll probably know it's 80 at that point. If you're teaching them this, they probably know that 40 plus 40 is 80. Yes?
Should we teach the kids to start in the ones place first?
Of course.
Or what?
Of course. I'm not going chronologically. I'm talking at some point, you would be talking about this problem, right? So, I mean, if you do that, what's 7 plus 6? 13. So then a student will say, what the shit's wrong with that? Then you put a 13 here. So that's where that comes from. It's a carryover from that. So this was fine before. Why is it not fine now, right? That's the question. So real quick, a quick way to tell them this is not quite right is an estimation approach. Right, so you should kind of try to introduce methods of estimation as you're teaching them, because that's the way you check to make sure that your answer makes sense physically. So if you say 40 and 40 makes 80, and you got 700 something, do you understand this could be, and that's when the kid's like, yeah, I can see that's a problem. Now, so what's a way you could write this where 13 would show up and it would lead to the right answer? I want 13 to show up and it would lead to the right answer. No. That wouldn't show 13. That would show a 3 with a little 1 somewhere else. I want 13 to show up.
What I was told is you break 13 down, but then on the 7 you put it underneath the 1.
Yeah, so 7 and 6 is 13. 30 plus 40 is 70. There you go. So 13 does show up. So this, let me stop for a minute. Is everybody with me? In fact, we've done exactly this before. We have done exactly this before.
Isn't that how you multiply double digits? Like by hand? Like something like that.
Well, yeah, multiplication is coming up. It looks like that, but for a completely different reason. Haven't we done this before? 30 and 40 is 70. 7 and 6 is 13. I know we've done exactly that before.
Yeah.
We've done exactly that before. Isn't that basically what I'm doing over there?
Yeah.
Do you see how that's a connection between one way of thinking about things and then an algorithm that we use? Because carry the 1, what the shit does that mean? What does that even mean? Right? What does it mean? So this is correct, but then how do you connect this with the accepted method that we use, which is not the only method, right?
Well, that's pretty well how you explain that the 1 is in the 10.
Say one more time.
Like you had already explained that the 1 is in the 10 place.
Good. I think you were there.
Where?
I'm sorry, go ahead.
Oh, the 1 is like the 10 is the 13 is in the 10th place, so we know that it wouldn't be in the 1 place because they are having no place value.
I like it. So the connection between this and the carry the 1, I think you're basically there. That 1 really is in the 10's place, right? And I know we all know how to add, yes? But we are now discussing how do you explain it to somebody who has never done it before in their entire lives, right? They're a very short life, normally, right? But still, they've never done it before in their entire life. If they understand this, then they can understand, okay, that's 13, put the 1 with the other 10s, because that 1 and 13 means 110. And that, of course, is explaining what that carry the 1 means, right? So if they understand this, they are ready to take the step to carry the 1. Ba-doo. Okay. I like it. Now here's a okay. There's and I should have looked this up. All right, we're gonna talk about a weird way to add. But has anyone ever seen another way to divide besides this method where you 7 into 3437 or something? Right, that's the way that most of us divide. Has anyone ever divided in a different
There's
setup?
some big 7, I think. A big one
The way
is,
that you did it, you mean? The one thing, that, yeah.
Oh, not with the manipulatives.
No, the one, I don't.
Okay, okay.
You just did it, I don't know.
All right, I can't
there
remember.
was a weird common core thing that was going around for, I think it's still to the younger grades, that I was looking at with my sister one time. I was like, what the heck is this? But I don't remember what it was.
So I'm thinking specifically, every now and again I'll have a student, and the students that come to mind are from Russia. And Russia is one of the few countries that uses a very different algorithm for long division. So I'm going to look that back up for next time. I should have looked it up for today, but I just want to show it to you at least once. Every time I have a student like that, and I ask them to show me, because I always forget. Because if you don't use it all the time, it's gone, right? Anyway. There is another method for, there's another algorithm for addition. And it's called the Lattice Method. Do you know the Lattice Method?
Yeah, my daughter was doing that.
Oh, okay, interesting, okay.
Not for addition though.
Okay, so say again? All right. So the method that we use to divide, to add, to multiply, those are all just one of many different methods we could use. The methods we've chosen aren't always the best, right? Always. But they're just the ones we chose. So the lattice method, let me see, what was the, oh yeah, 37 plus 46. Let's try that real quick. 37 plus 46. Oh, let me make this bigger. So if I draw a little, so here's what's weird about the lattice method. Okay.
I remember it.
You remember it?
Yeah, a little bit.
Do you remember, where did you learn it?
Maybe I'll put
When you were, I mean, you know what I mean, like what age, what grade? Like way a long time ago?
That's crazy.
Way a long time ago?
Yeah.
Okay, okay.
Fifth grade?
I didn't think you went down at the 7-Eleven.
No.
That's fine, some soda, and the guys, look at this shit.
Oh, no.
That would be interesting. All right.
Okay, that's crazy.
7 plus 6 is 13. 3 plus 4 is 7. Oh, 7, right? Okay, let me stop for a minute. Does everybody see what I just did? Now you add diagonally. So 0. 1 plus 7 is 8. 3.
Yay.
See how that's, you 7 and 6 is 1, 3. Do you see how these are like the places, right? The 10's place, the 1's place.
Yeah.
3 and 4 is no 10's, 1, 7, of course, right? And then you add diagonally. That's why you draw these little things, because it kind of makes this into a diagonal. 1 and 7 is 8. 3 is 3.
Oh, wow.
Maybe?
It's
No.
crazy.
Do you see how this is the same thing as carrying the 1? Didn't the 1 just sort of come over here?
Yeah.
But it looks completely different, right? All right. You guys try this one real quick. Try to do 123 plus 335.
So would you need to draw more?
Yes. Now you need 3 of these bad boys. Yes. Oh no, Jeff, come on.
Wait, 3 dash.
That's gonna take so much of my life to do it.
Can you just draw with a rectangle?
What's that? What?
But I don't know what to draw.
Oh, okay. So for each spot, well, I don't know why I put it way over there. For each spot, you've got a block, and then you just bam, bam, bam. Right. So for each spot, you got a little diagonal block. So this one's kind of boring, right?
Yeah.
3 plus 5 is
8.
so
0,
8. I like it. 2 plus 3 is
5, 0, 5,
I like it. 1 plus 3 is
0, 4.
I like it. So then 8, 5, 4.
Something light.
Let's try one more, and of course this time I got to make it worse because now I feel like everybody. What's up, sorry? Everybody okay?
I think I added too many blocks.
Oh.
Sorry.
I'm not getting I think that's because you're not a 6-year-old. Bro, this blew my mind. Like, this blew my mind.
I'm really glad.
This is good.
I just missed something.
He
has a
very
connection
passionate
with
about this.
this
No, I love it.
Lattice Method.
It's so
I'm
nice
not
to
very
not be the
passionate
only
about
person in the room.
I'm having
I'm
my
having a
second
meltdown.
graders would be having a meltdown right now.
I would be having a party. I don't know what you're talking about.
I'm already upset and everything. Not one.
All right, how many blocks do I need here?
1, 3.
3. Something interesting's gonna happen though.
Diagonally. Yeah, but I didn't.
Hold on. I'll try to make it more clear.
I don't like
All right, guys.
this. Now I got 10 again.
Guys, here we go. What's 4 plus 8?
I want the number, but I got the number.
1, 10, 2 1s, right? Aw, you're dead. All right, right? 12. Okay. 7 plus 2. Right? Right?
Yeah.
Okay, does everybody see that? What's happening? Okay, okay. 8 and 3. Now, these set up avenues. What do you mean? Sorry.
Draw the diagonal line out. Yeah.
Sure, okay, you can.
Sure.
2, right? 2 is the only thing here, yes?
Yes.
10.
But you have to put the one up.
You're just having the same problem
On that
again.
corner, just add it to the corner.
Yeah.
But the same
0.
thing is.
2,
Yeah.
1. Yeah, I know.
Yeah.
I didn't say it alleviates troubles. Did
It makes it worse.
I? All right.
Just like all these extra steps.
Why are y'all hating?
All right. Guys, calm down. Do you suddenly have to do this everywhere in your life now?
Yes.
Do I have that kind of, if I had that kind of control, I don't know if I should have it. You must do it this way, everything. No. All right. So calm down. Does it make sense?
Yeah.
Does it address every issue that's ever existed with addition? No. Is it a different way to? It does. No. You're always concerned. It was you.
It's for kind of a safety net, it would be this not.
Just call me
Yeah.
Jordan for
The only thing if you're
I'm not
drawing
an
out
art
what
major.
you would write out.
Yes. Okay. Yes.
If we're doing it for this method, you could also just write the line straight down through the 10's ones place. It'd be the same thing.
Not really. No.
Well, it's not like.
This.
Wait.
Anyway, all right, guys. This is just another possible way to add things. Every possible way you can conceive of to add two numbers, are they gonna be like completely different, or should they all share something? Yes, they all should share something, because they're all just adding numbers, yes?
Yeah.
All right, so the important thing is, not that you love this, not that you wanna use it for the rest of your life, but that you understand it, that it makes sense. So this one kind of builds in some of the carrying stuff. Not all of the carrying stuff, but it does build in some of the carrying stuff. The lattice method, oh yeah. Oh yes, the lattice method for multiplication. We'll see how that works. Okay. All right. I'm not even saying that your curriculum, wherever you end up teaching, is going to require you to teach the lattice method to your students. Yeah. I'm not even saying that. I'm just saying this is another thing. Do you have students that will come into your classroom that were in other districts before they came to you?
Yeah.
Yes. Do you have students that might come in there having been taught the lattice method?
Yeah.
Would they be concerned, or should you feel bad if you're not even sure how to tell them what the lattice method and how to go to the other method? You might, right? So you should be aware that these things exist at the least, right? Okay. All right. Let's see. What else can I completely bum you out about? Oh. So let's talk about multiplication, because I basically already talked about subtraction with the manipulatives, and that's kind of nice when you can visually see what's happening with the subtraction. Let me make sure I didn't skip anything with, I don't think so. Not really, no. Okay. I like it. Yeah, they sort of have. All right, let me do this one thing here with subtraction. I got a nifty, what is my example? 323 minus 64. So I'll have, using base 10 manipulatives, blah, blah, blah. I'll have 323. And I've got to subtract 64 from this. All right, so let me just put 60. So this is 323. 3, Jeff. What did I just do? You guys, it's fun. Maybe I'll be okay. And then 64. So we sort of addressed this earlier. I just want to kind of bring this back real quick, just to give us a method that I think we might like better than lattice, hopefully, I don't know. So what would I do first here? Yeah. What would you borrow from? Yeah, let's see. So I can take one of these.
Wait, no, 10.
Oh, you want to start with the tens?
Yeah.
All right. So, well, here's the thing.
We're gonna have to do it.
We totally could start from there, believe it or not. We totally could.
I just learned to go
We're gonna have to do it.
Yeah, we can do that. We can do that. So if I take one of these, sure, that'll make this into that. But eventually I'm going to have to do that anyway. So when you have a visual like this, you don't have to stick with the algorithmic method that we know. You can actually kind of play with it a little bit. Okay. So then this will be 13 minus 4. 9. So again, they would do this. There's 4. There's 4. They count what's left. 9. And of course here, can't do this. So then I'll do, I was trying to do wrong. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So now I got 11. So they would do 1, 2, 3, 4, 5, 6. And they would find 1, 2, 3, 4, 5, 6. And what are they left with? 4. Does that make sense, Chef? I don't know. Did it count correctly?
It's 5.
It's 5.
I was
What did I leave one off? This is why it's better to use an actual manipulative. Okay. 5. And then I got 2. All right. I was going to show you a different way. That's okay. That's okay. I can let it go. I can let that go. Let's talk about multiplication. And we're sort of trying to work towards the way that we multiply, where we actually carry the 1 and all that kind of stuff. Just remind me again, what's the first method we could use to do this? What's another way we can kind of do this directly, not this way? We can kind of use the places. This is a little more.
Are we doing it that way or the way we learned yesterday?
So like, yeah, the way that we did it before.
So 30 times 12 and 4.
Yeah, you could, okay, so you could do 30 times 12 plus 4 times 12, right? Is that all right?
Yeah.
You could totally do that.
30 times 10.
Say again?
30 times 10.
30 times 12. Oh, are you talking about a different way?
Yeah.
You could break it down even further, and you could say 30 times 10. Now, here's where you gotta be careful though. If I do 30 times 10, and let me write this out for you, because you can lose some stuff. Real quick, just to make this finished, what would this be?
360.
360 plus
48.
48? 408. Okay, so if I took 34 times 12, this will be 30 plus 4. This is 10 plus 2. Okay, because you could lose some stuff if you're not careful, the cross products. So then you could do 30 times 10. And you could do 30 times 2. 4 times 10. Make a consistent Jeff, and then plus 4 times 2. Okay. So if you didn't put that down for yourself, you could very easily miss one of these guys in the middle. Now, what we're trying to work towards is a way to, of course, the way that we do it right now, which is we don't even think about this being 30 necessarily. It's just part of the algorithm that we go through. But they're not going to be ready for that from the beginning. And of course, this gets to the same place, right? 300 plus 60 plus 40 plus 8, so it's still 408. I love it. Thank you, guys. Oh, okay, now. All right. I like it. So why not continue with the tradition of math teachers and bring back the thing everybody really liked. Let's do this lattice method. Right. I know you guys desperately want to see what this looks like in a different way. Okay. So the way this is going to work now is I'm going to put 34 and I'm going to put 12. Become a thing. Now I want you to notice where things are coming from here. I think you guys are going to like this better than the addition one. Yeah.
Can I put the 1 and the 2 on the left side? Or is
You
that?
totally could.
Okay.
Yeah.
I didn't know if there was a rule or something.
I think you can. This is the way that I know how to do this. There are other ways to set this up. There's totally different ways to do almost everything we do. But now you just kind of, this feels kind of like just a multiplication table in general. So like, how would you figure out what goes here when you do 2 times 2? Okay, so this is 1 times 4. Isn't that 04? What's this? 2 times 4? 0.8. So what's this? Yeah, 0.3. And then what's this? 0, 6. I like it. And then you have the same way we did before.
Diagonal?
The diagonals. That's why I try to make this. So let me make sure you understand where the diagonals are coming from. Here, 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 right? So this will be 8. 4 and 6 is 10. 4. I like it. And again, I don't know. You guys want to do it like this, don't you? Sorry. Let me do it the way you guys seem to like. So you could do 8. Then this will be 10. And this will be 4. Is that better?
That place.
Yes? Okay. Can you forgive this there this time maybe? Because now we're multiplying, so it's, you know. Okay. No? Maybe? No? We're still adding, we're still carrying, we're still doing stuff. All right. To be really honest, I think the lattice method depends. I don't think there's like a general California education rule about lattice method. But it kind of depends on which school district you end up working at. And it could depend on which school you end up working at, what they want you to show the kids. What about, yeah, we sort of did that, but I want to show this again. Yeah, let's do 2 more things, and then we'll call it a day. So just to remind you, this might be easier to do just drawing it out. So 461 divided by 3. All right, so that'll be 4. Let's see if Jeff can do it this time. There you go, buddy. 61. So again, this is the best method to show somebody who doesn't know division. This is where you want to start. This is nice and visual. There's no guessing about what's going on. There's no guessing what to try. You can just see it exactly. So what's division by 3 mean? I'm looking for groups of 3. So in my hundreds, I have how many groups of 3? 1. So what do I have to do with this guy?
Split them up.
Split him up. He's left over, poor little dude. So he's going to become 10 of those. How many groups of 3 do I see here now? I see 1, 2, 3, 4, 5. Yes? Okay, I like it. So there's a 5. And then what do I do with the poor little dude left out?
Break them up.
Break him up. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So how many groups of 3? 1, 2, 3. Okay. 3 groups of 3, and then remainder 2. Is that correct?
Yes.
Yes.
Wait.
Soon. Go ahead.
Oh, never mind. Yeah, I got it.
What's up? Is everybody all right? All right. Did I win some of you back over that were hating me about the lattice stuff?
Yeah.
Okay. What does remainder 2 mean?
There's 2 leftovers.
What does it mean?
There's a decimal afterwards.
Okay, it would be a fraction, it would be a decimal part. But what it means is, if this was 2 smaller, 3 would have went in evenly, right? So remainder tells me how much more this was from something the divisor would have gone in evenly. Maybe? Did you guys do in algebra? Did you ever divide polynomials in algebra?
Yeah.
The remainder meant the exact same thing. So, oh shit, Jeff. Okay. Tiny bit of algebra. Can we just do like? All right. Just what is this? Can somebody, right? We can do that, right? What is that?
X
Square. 5x.
squared. 5x. 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 5x.
right? 5x and 4x, is that cool?
Yeah.
And then of course plus
20.
20. So now watch, you guys know this. You ready? I'm gonna put something really funky up here and you're gonna know the answer, no problem. What do I get if I divide x squared plus 9x plus 20 by x plus 4? There's no work to do.
X plus 5.
It's x plus 5.
Oh.
Think about it. What's 10 divided by 2?
It's like
5.
a missing-
Why? Because 2 times 5 is 10. So I know that this times this is this, therefore this goes into this many times. Now, what do I get when I do back?
X plus 5, remainder 4.
Yeah, x plus 5, remainder 4. Now I'm not going to quibble about, that's not the way we would write it, but isn't this 4 more?
Yeah.
Yeah.
So the remainder means the same thing. I'm sorry. I just had to. But I like that. All right. So leave that behind. It's okay. So this thing, all right. This thing is neat. Again, I love this thing, this idea, because it's so visual. Yes.
You know how we have the same like factors for multiplication? When you have like 10 times 20. Oh, right, like 10 times 2 is 20, and you have divide 20 divided by 2 is 10. It's the same thing for like
Yeah,
that,
it's the
right?
same thing.
But
Yeah.
what is that called when you have like it's not the missing additive? That's multiplication and addition. What is this then?
Oh, the way I would write this. All right, this is
Like, what
doesn't.
is it called?
This doesn't really answer your. Hold on. If I rewrite this, you might think of the answer yourself. I mean, it doesn't really have a. Remember, I mean, even our book, this would be the quotient, and this would be the remainder. I mean, that's. Okay. Isn't this equal to this times this plus 4? It's got an extra 4 that I threw in there, so that remainder makes immediate sense. It's just 4 more than it would have been to go in evenly. Okay. Now, last thing for today. All right, look at that. Yeah. We're not going to do this, of course. I know we all know the long division. We're going to do kind of the precursor to that. Precursor meaning the what would come before that, what you want to show students to lead them in this direction. So, how many 31s approximately are in 5,700? What's a better way to look at it? Actually, any guess will work. Give me a good guess. How many 31s are in this? Give me a guess. It's definitely not 20. 20 is too much, right? Does everybody agree with me that 20 is too much? That'd be 6,000 something. Let's say 10.
10.
Let's say a horrible guess. Everybody agree that 10 is a horrible guess, but it's still something. Stay with me. What happened over there? I missed it. All right, I'll let it go. So let's say 10 31s. What is 10 times 10 31s? 100 31s, right?
Yeah, let's do 100.
That's better. 100 31s. What's 100 31s?
3,100.
1,000. Wait, sorry, 100. Yeah, 3,100.
3,100. So the whole 10 thing earlier, we need 100, right? Because we're talking about something on the order of 1,000. All right, subtract that. Now, is this the way we do division? Is this the real way we do division? No. But stay with me. Again, this is not the end algorithm. This is a middle step, right? So how much is left to be taken care of? 2639. All right. So give me another guess. Oh, let me put you next to this. Sorry. There we go. That is what can that come from?
10.
So let's say 10 31s. 10? No.
100 again?
100 would be too much, right? So let's say 50.
Oh.
Why not? Let's say 50. Somebody tell me real quick, if 100 31s is 3,100, what's 50 31s? Half of this. 1550. So this will be do you think now? How many 30s? Give me a guess. Go with 31s. Go with that. How many 31s do you think? What's 3 31s? 93. So what's 30 31s?
What?
If 3 31s is 93, 30 31s is 30, right? Just add an extra 0. So let's say 30 31s. So that's 930. What do we got left here now?
159.
Okay. And then this is not too bad, right? How many 31s in 159? What do you think?
4, 5.
Let's say 5, right? Because what's 5 times 30? 150. What's 5 times 31? So there's a remainder of what? How do I know that I can stop here? Because that is smaller than that. Ain't no 30s going in that thing. Okay. All right, what do we get? So what do we get here then? 150, 180, 185. So 185 remainder 4. Is that the right answer? 185 remainder 4. What's 31 times 185? Somebody help me out. 31 times 185.
5,735.
If you add 4 to it,
Yes.
do you guys understand that's the right answer? Yes? Okay. Has anyone ever seen this weird thing? Yes, a little bit? Yes? And again, this feels weird to us because immediately it felt weird to us because that's not right. That's not right, but it's fine. It's not a complete algorithm that we use, but it is an algorithm that, would you agree? This is an algorithm that works?
I feel like it takes more work than the actual.
Say again?
It
Sorry?
takes more work than actual.
Oh, true. Yeah, good point. But again, there's a lot in there that students aren't immediately going to understand if you don't take steps like this. This I can get a hold of. I'm like, okay, this much took care of that. Okay, this is left to take care of. That takes care, okay, that takes care of. You can see it happening, and then you build to the actual algorithm. Okay, that's enough. I've tortured you today. Well, some of you love the torture.